This galaxy is wrong. According to everything astronomers thought they knew about how galaxies are built, when they're built, and what they're made of, this object should not exist. Its name is JADES-GS-Z14-0, and it's sitting at the edge of the observable universe like a fact that refuses to behave. When the James Webb Space Telescope launched in late 2021, scientists had a specific job in mind for it. They wanted to see further back in time than any telescope had ever seen, to peer past Hubble's reach, past the era of mature galaxies, all the way back to the moment the universe first lit up. Webb was built to find the first galaxies, the proto-galaxies, the dim, scattered, half-formed clumps of gas and the earliest stars struggling to ignite in a cold, dark universe. That was the prediction. Small things, faint things, things that would barely register against the noise. The first deep observations told a different story. To understand why this matters, you need to know the rules. After the Big Bang, the universe was a hot, expanding fog of hydrogen and helium with traces of lithium. Nothing else. No carbon, no oxygen, no iron, no rocky planets, no anything. For the first 380,000 years, the universe was so hot that atoms couldn't even hold themselves together. When it finally cooled enough for hydrogen to form, the universe went dark. Astronomers call this period the cosmic dark ages. Picture an entire universe of black, lukewarm fog. No stars, no light, just gas drifting outward, slowly clumping together under the pull of gravity. Eventually, somewhere between 100 and 250 million years after the Big Bang, the first stars finally flickered to life. They were enormous, blue, short-lived. Astronomers call them population 3 stars, and we have never directly observed one. Some of them may have been hundreds of times more massive than our Sun, burning so hot and so fast that they only lived for a few million years before going supernova. They burned hydrogen into helium, helium into carbon, carbon into oxygen, building heavier elements deep in their cores. Then they exploded. Their guts seeded the surrounding gas with the first heavy elements in the history of the universe. From those enriched clouds, the next generation of stars formed. From those stars, galaxies began to assemble, slowly, in pieces, over hundreds of millions of years. That's the standard story. That's what physics says happened. Then Webb pointed its mirror at a tiny patch of sky in a region called the Goods South Field, and it found JADES GS-Z14-0. The name itself tells you what was happening. JADES stands for the JWST Advanced Deep Extragalactic Survey, a coordinated international program designed to push Webb to its absolute limits. Hundreds of hours of telescope time, dozens of researchers, and one shared goal. Find the first galaxies. Map the moment the lights came on in the universe. The team expected to find faint, scattered, primitive objects sitting at the edge of detectability. What they found instead was something that nearly broke their data pipeline. The galaxy was so bright at such an extreme distance that some on the team initially assumed it had to be a closer object whose light had been distorted into looking more redshifted than it really was. It wasn't. Follow-up observations confirmed the distance. The galaxy is exactly where it appears to be, and it is exactly as bright as it looks. The galaxy sits at a redshift of 14.32. If those numbers mean nothing to you, here's what they translate to in plain language. The light from this galaxy has been traveling toward Earth for about 13.5 billion years. We are seeing it as it existed when the universe was only 290 million years old. Barely a toddler. Less than 2% of its current age. Redshift is the universe's way of telling us how far away something is. As space itself expands, the light traveling through it gets stretched, shifting toward the red end of the spectrum. The further away an object is, the more its light has been stretched, and the higher its redshift number. A redshift of 14 is not a small adjustment. The original ultraviolet light coming from this galaxy's young, hot stars has been stretched so dramatically that by the time it reaches Webb, it arrives in the infrared. The light we are detecting today is 15 times longer in wavelength than when it left. And yet, there it is, fully formed, hundreds of millions of stars, a diameter of roughly 1,600 light-years, bright enough to be picked up across nearly the entire history of the universe. For comparison, our own Milky Way is about 100,000 light-years across and contains hundreds of billions of stars. JADES-GS-Z14-0 is smaller, but it's also far younger. It's not the size that's the problem, it's the fact that it exists at all. To understand why Webb sees what Hubble couldn't, you have to understand the technique. Astronomers call it the dropout method. As light from the most distant galaxies stretches into the infrared, certain wavelengths get absorbed by clouds of neutral hydrogen drifting through intergalactic space. The result is a clean, sharp cutoff in the galaxy's spectrum. On one side of that cutoff, you see light. On the other side, nothing. By looking for that fingerprint at progressively redder wavelengths, astronomers can identify how far back in time a given galaxy is. Hubble could see the dropout for galaxies up to a redshift of about 11, which translates to roughly 400 million years after the Big Bang. Beyond that, its instruments hit a wall. The infrared signal got too faint, the wavelengths too long. Webb was built specifically to break that wall. It worked. Imagine planting a seed in a flower pot, walking away, and coming back 10 minutes later to find a full-grown oak tree. Not a sapling, not a young tree, a massive, mature oak with deep roots and full branches. That's the scale of the contradiction. Then there's what Webb spectrometers detected inside the galaxy itself: oxygen. That single word changes everything. Oxygen is not a primordial element. It cannot exist in significant amounts without stars first being born, living their lives, fusing lighter elements into heavier ones in their cores, and then dying in massive supernovae that scatter those heavier elements into space. Every oxygen atom in your body, in the air you breathe, in the water you drink, was forged inside a star that died. So when astronomers detect oxygen in a galaxy that we are seeing only 290 million years after the Big Bang, the math gets uncomfortable. It means stars had already been born inside it, lived their lives, died, and enriched the surrounding gas with heavy elements, all within a window of time that should not have been long enough for any of that to happen. The detection itself was made by an instrument called NIRSpec, the near-infrared spectrograph mounted aboard Webb. NIRSpec doesn't just take pictures. It splits incoming light into its component wavelengths, the way a prism splits sunlight into a rainbow. By looking at where the dark and bright lines fall in that spectrum, astronomers can read the chemical fingerprints of whatever is producing the light. The signature for doubly ionized oxygen showed up clearly in JADES-GS-Z14-0. Not a smudge, not a guess, a signature. The early universe, according to current models, was supposed to take its time. Stars were supposed to form slowly. Galaxies were supposed to assemble piece by piece. This one looks like it skipped steps. And it's not alone. In the years since Webb came online, astronomers have found a steady, growing list of galaxies at the edge of the universe that don't behave the way the rules say they should. Some are too bright. Some are too massive. Some have stars older than the galaxies themselves seem to allow.
There's JADES-GS-Z13-0.
sitting just slightly closer in time, but still firmly in the Dark Ages window. There's ZEERS 93316, briefly thought to be even further until follow-up observations revised its position. And then there's GN-Z11, an object so unusually luminous that it appears to harbor a supermassive black hole, weighing roughly 1 million times the mass of our Sun, sitting at its center, when that black hole shouldn't have had time to grow that large. This isn't a small problem. The number of galaxies that don't fit has been climbing every year since Webb began operations. Astronomers have a name for the growing tension between the data and the theory. They call it the impossibly early galaxy problem. There are essentially 3 possibilities, and none of them are comfortable. The first possibility is that the standard model of cosmology, the one that has guided astronomy for the better part of a century, has something wrong with it. Maybe the universe is older than we thought. Maybe the rate of expansion was different in those first few 100 million years. Maybe dark matter, which has never been directly observed, behaved differently in the early universe than we assumed. The standard model relies heavily on dark matter pulling ordinary matter together into halos that then collapse to form galaxies. If that process happened faster, or if dark matter clumped together more aggressively in the early universe, galaxies would have had a head start no one accounted for. If that's the case, every textbook in the world might need a footnote that says the foundation underneath might be cracked. The second possibility is that our models of how stars form are wrong. Maybe the first generation of stars was not just enormous, but ferociously efficient. Maybe entire galaxies could ignite and mature in tens of millions of years rather than hundreds. Maybe the chaos of the early universe allowed for a kind of stellar wildfire we have no real analog for today. Some simulations suggest that without dust and heavy elements to slow them down, the first molecular clouds could have collapsed and ignited stars at a rate 10 or 20 times faster than what we see in the modern universe. If that's true, the cosmic dark ages may have ended a lot more abruptly than anyone expected. The third possibility is the strangest of the 3. Maybe some of these early galaxies are not glowing because of stars at all. Maybe their light is coming from something else. Supermassive black holes feeding on infalling gas. Direct collapse seeds, where a giant cloud of gas skips the stellar phase entirely and becomes a black hole the size of a small galaxy core all at once. The gas around such a black hole, heated to millions of degrees as it spirals inward, can outshine entire galaxies of normal stars. If that's true, what we're looking at when we point Webb at the early universe might not be galaxies in the traditional sense. They might be monsters in disguise, fed by primordial accretion at a rate that ordinary physics struggles to explain. The direct collapse idea is worth pausing on, because if it turns out to be correct, it solves more than one mystery at once. We already know that the universe contains supermassive black holes weighing billions of times the mass of the Sun, and we already know that some of them existed less than 1 billion years after the Big Bang. The standard explanation, that they grew slowly from stellar mass seeds, has always struggled with the math. There simply wasn't enough time. But a direct collapse black hole could start out at 10 or 100,000 solar masses, giving it a massive head start. If those exotic objects formed throughout the early universe and are now showing up in Webb's images disguised as bright young galaxies, the timeline finally starts to make sense. The trade-off is that we would have to accept the existence of an entirely new class of object that we have never directly observed. If you were somehow standing inside JADES at the moment we're seeing it, you wouldn't see anything resembling a sky like ours. The background of space would still be glowing faintly with the leftover radiation of the Big Bang, like a hot ember slowly fading. The galaxy around you would be packed densely with young, blue, hot stars, blazing in ultraviolet light, choking on the dust and gas thrown off by their dying neighbors. The sky would feel close and violent, a pressure cooker of star formation. There would be no familiar constellations, no quiet nights. The radiation alone would be enough to sterilize anything that resembled biology before it could even begin. Nothing like the slow, calm, ancient universe we live in today. And the strangest thing is how common this is becoming. The deeper Webb looks, the more of these objects appear. They might be the rule we never knew about. The reason this matters, beyond the obvious thrill of discovery, is that cosmology is the foundation underneath everything else in physics. The age of the universe, the rate of its expansion, the formation of structure, the behavior of matter at the largest scales, all of it rests on a model that is now being tested by data it was not built to explain. Webb was supposed to confirm what we already suspected. Instead, it keeps finding things that don't fit. There's already a related crisis brewing in cosmology that this discovery might be connected to. It's called the Hubble tension. When astronomers measure how fast the universe is expanding using nearby objects, they get one number. When they measure it using the leftover radiation from the Big Bang, they get a different number. Those two numbers should agree. They don't. The disagreement has been growing more statistically significant for years, and no one has been able to explain it cleanly. Now, Webb is showing us early galaxies that seem to have grown up too fast. Some physicists think these problems might be linked. That whatever is wrong with our understanding of cosmic expansion might also be what's making the early universe look so unexpectedly mature. There's another wrinkle that makes this more interesting. The end of the cosmic dark ages was supposed to be a slow, gradual process. Astronomers call it reionization. As the first stars and galaxies turned on, their ultraviolet radiation began stripping electrons off the neutral hydrogen filling space, turning the universe transparent again. That process was supposed to take hundreds of millions of years, with the universe slowly clearing up like fog burning off a valley at sunrise. But if galaxies like JADES-GS-Z14-0 were already this bright and this developed at 290 million years, the timeline gets compressed. The fog burned off faster than anyone thought possible. Whatever was producing all that ultraviolet light was either wildly more efficient than predicted, or there was simply more of it than anyone thought existed at that moment in time. If you could rewind your view of the universe and watch reionization happen at high speed, it would look like sparks catching across a dark plane. First, a single point of light, then another, then dozens, then thousands, each one carving out a slowly expanding bubble of clear space around it as its radiation pushed back the fog. Eventually, the bubbles overlapped, merged, and the entire universe became transparent. JADES is one of those first sparks, only it's burning so brightly that something about the picture doesn't add up. Some astronomers are calm about this. They point out that science always finds anomalies. Every major telescope ever built has produced results that didn't match expectations, and most of those results eventually got absorbed into refined theories. They argue that with more observations, more spectra, more time, the picture will sharpen and the contradictions will resolve. They might be right. Others are less calm. A growing number of cosmologists are willing to say, in print, that the standard model may not survive the next decade in its current form. That something fundamental about how we describe the universe's first chapters might need to be rewritten. They aren't panicking, but they're no longer comfortable. Enter the next wave of instruments designed to dig deeper into this mystery. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will survey enormous patches of sky at infrared wavelengths. hunting for thousands more high redshift galaxies to compare against the handful we have now. The extremely large telescope being built in the Atacama Desert in Chile, with a primary mirror nearly 40 meters across, will give us ground-based detail at a resolution never achieved before. Together with Webb, these instruments will turn what is currently a small statistical sample of impossible-looking galaxies into a population study. If the early universe really did make galaxies faster than physics predicts, we will know it for certain within a decade. If something else is going on, something we haven't even guessed at yet, we'll have the data to start asking the right questions.
In the middle of all of this sits JADES, indifferent to our confusion. A faint smudge of ancient light captured by a telescope a million miles from Earth. A galaxy that doesn't care whether it's supposed to exist. It just does.
We built Webb to answer questions about the early universe. We didn't expect it to ask questions back. We didn't expect it to hand us evidence that maybe, in those first few 100 million years, the universe was doing things we still don't have the language for. Things that contradict the careful timelines scientists have spent decades constructing. Consider what this galaxy is actually telling us. The light arriving at Webb's mirror today left its source when the universe was a fraction of its current age. That light has crossed expanding space for 13.5 billion years.
Along the way, the universe stretched. Stars formed and died by the trillions. Galaxies merged. Planets, including ours, condensed out of dust. Life arose on at least one of them. Civilizations rose and fell. And the entire time, that single beam of ancient infrared light kept moving, undisturbed, carrying with it a snapshot of a moment we have no other way to see. When it finally landed on Webb's gold-coated mirror, it was less than a whisper. The instrument had to stare at the same spot for hours, sometimes days, just to collect enough photons to know there was something there at all. That's the kind of patience this work demands. Not days, not years, lifetimes of staring into the dark, waiting for the light to come. And what came back was a contradiction. There's a line that some physicists like to use when something unexplained shows up in the data. They say nature is under no obligation to make sense to us. JADES feels like a reminder of that. The universe is not waiting for our models to catch up. It is simply being what it is, ancient and strange and stubborn, and inviting us to figure it out at our own pace. Every textbook, every simulation, every careful prediction has to be measured against what the telescope actually sees. And right now, what the telescope sees is winning. There's also something humbling about being the first generation of humans able to look at this part of history at all. For 99.9% of human existence, the night sky was a flat ceiling decorated with stars. For most of recorded history, even our greatest astronomers had no concept that other galaxies existed beyond our own. Less than 100 years ago, Edwin Hubble first proved that the smudges of light we called nebulae were entire other galaxies, vast islands of stars far beyond the Milky Way. Now, in the span of a single human lifetime, we have gone from not knowing other galaxies existed to questioning whether the rules of galaxy formation themselves are correct, based on light from the very first ones to ever shine. That progress is staggering, and JADES is the latest punctuation mark in that sentence. Whether the standard model bends or breaks in the coming years, one thing is clear. The early universe was not the slow, dim, well-behaved place we drew on the chalkboard. Something else happened. Something faster, something brighter, something that fit a galaxy where there shouldn't have been room for one. We're not at the end of this story. We're somewhere near the beginning, holding a flashlight, staring at a single piece of evidence that doesn't fit, and slowly accepting that the picture we drew of our own origins may have been incomplete from the start. That's it for this video. Thanks for watching, and I'll see you in the next one.